You know, from the phone in your pocket to the traffic lights on your street, our entire world runs on this invisible architecture of code. But we're not just talking about apps and websites here. A lot of the time, this stuff is literally a matter of life and death. So let's pull back the curtain on the invisible discipline that builds the software we can, or maybe more importantly, can't trust. And this right here is the big question, isn't it? When a software failure isn't just, an annoying glitch, but a potential catastrophe, how in the world do engineers build something that has to work perfectly every single time? Okay, let's make this real. Think about a personal insulin pump. I mean, it's an incredible piece of technology, right? It's constantly tracking blood sugar, it's calculating the exact dose of insulin needed, and then it delivers it. This is what we call a safety-critical system. A software glitch, a tiny miscalculation, just one little bug, and the consequences are absolutely dire. We're talking coma, or even worse. The software has to be dependable. So yeah, this question isn't some abstract thought experiment. It's a real-world engineering problem with the highest stakes imaginable. So to really get how we build software you can trust, we first have to understand why it's so different from, well, building a bridge or a car. I mean, it's not a physical thing you can touch or see, and that changes everything. All right, here's the absolute key difference you've got to get. Hardware, a physical part. It wears out. Think about the brakes on your car. They have a pretty predictable lifespan. Engineers can even map this out on something they call a bathtub curve. But software, it's a totally different beast. A line of code doesn't rust, it doesn't get frayed, it doesn't wear out, it deteriorates. See, every update, every new feature, every time you connect it to some new system, you run the risk of breaking something that used to work just fine. Its biggest enemy isn't time, it's change. And because software is so weird and unique, a whole bunch of really dangerous myths have popped up around how it's made. And these aren't just harmless little misunderstandings. No, these are the kinds of myths that lead to bad decisions, projects that go completely off the rails, and products you just can't rely on. So let's bust a few of these, shall we? First up, the myth that once we write the code, we're done. Oh no. The reality? A truly staggering 60 to 80% of all the work happens after the software is first delivered. That's maintenance, updates, you name it. Then there's this idea that you can't know the quality until it's running. That is just plain wrong. Things like formal technical reviews can spot major flaws in the design right at the beginning. And my personal favorite, the myth that a proper process is just a bunch of red tape that slows you down. Nope. The truth is, when you focus on quality from the start, you cut down on rework, which is what actually makes you deliver faster in the end. And all of this really gets to the heart of it. The real problem, the big challenge of making great software, isn't just about hammering out lines of code. It's about managing this immense, constantly shifting complexity. And to do that, you need a totally different way of thinking. And that way of thinking? Well, it has a name: software engineering. This is the formal, structured discipline that's designed to bring some order to the chaos of software development. It's how we go from something that feels like a garage hobby to a true professional practice. And the official definition from the IEEE really nails it. Let's look at the keywords here: systematic, disciplined, and quantifiable. This isn't about just winging it or having a gut feeling. It's not about just hacking something together until it kind of works. It's about applying proven engineering principles to the act of creating software, building things that are meant to last. You can actually think of this discipline as being built in layers. Right at the bottom, the absolute foundation for everything is a focus on quality. On top of that, you build a process. That's the framework, the who does what and when. Then you have your methods. These are the technical how-tos for actually building the software, like design and testing. And then finally, at the very top, you have tools, which are there to automate and support that whole structure. See, you can't just grab a fancy tool and expect magic. You need the whole foundation underneath it. Okay, so what does this layered approach actually look like in practice? How do real engineers use this stuff to build something like that insulin pump we talked about? Well, almost any professional project is going to follow a generic framework that looks something like this. It always starts with communication. I mean, you have to really understand the problem you're trying to solve. Then comes planning, creating a roadmap for the whole project. After that is modeling, which is kind of like creating the blueprint or the architectural sketch of the system. It's only then that you move on to construction. That's the actual coding and testing. And finally, you have deployment, which is when you deliver the finished product to the customer. It's just a logical flow, right? From a simple idea to a working reality. But, if all those steps and frameworks seem a little Complicated? This quote from the mathematician George Polya really brings it all back down to earth. Because at its core, engineering isn't really about frameworks or fancy tools. It's just about solving problems. And the connection here is just perfect. Decades ago, Polya laid out 4 super simple steps to solve basically any problem. Step 1, understand the problem. Hey, that's our communication step. Step 2, plan a solution. That's our modeling and design. Step 3, carry out the plan. Well, that's construction. And step 4, examine the result for accuracy. And that's testing. See? Software engineering isn't some bizarre new science. It's the classic art of problem solving, just applied to a very modern, very complex challenge. So after all this work, all this discipline, these layers, this problem-solving process, what's the actual goal here? What does good software even look like at the end of the day? It really boils down to these 4 essential things. First, maintainability. Can it change and evolve without completely falling apart? Because we already know change is the one thing you can count on. Second, dependability and security. Is it reliable? Is it safe? Can it protect itself from attacks? Third, efficiency. Does it waste resources like memory and processing power? And finally, acceptability. Is it actually usable and understandable for the real people it was built for? You can't just have 1 or 2 of these. You need the whole package. And that brings us right back to where we started. This whole discipline, from that foundational focus on quality all the way up to the detailed process, that is the answer to our original question. That is how you build a safety-critical device like an insulin pump that works every single time. It's not magic, it's just good engineering. But of course, the challenges never, ever stop. We are moving headfirst into an era people are calling open-world computing, where just countless devices are all constantly talking to each other over these huge wireless networks. As literally everything gets connected, our cars, our homes, you name it, the complexity and the stakes are just going to get higher and higher. The fundamental principles of engineering will still be there for sure, but how will they need to change and adapt for this new, hyper-connected world? Well, that's the next great problem for us to solve.